Okay, friends, good morning.
Good morning, sir.
Let us pray. Okay, friends, some of you have not muted your microphone. Some other sounds I also heard. Eh? So try to mute. Okay, friends, last day we had seen atomic mass. Okay, atomic mass, as you know, is not the actual mass of an atom in gram or kilogram or any other unit. But it's only a relative mass. If it is a relative mass, we should have something for comparison. We should have something for comparison. So a standard is needed to express the atomic mass. Okay, let me ask you a question. What is the modern standard for atomic mass? You can answer. What is the modern standard for atomic mass? Come on.
Carbon 12 isotope.
That is say it is carbon 12. The modern standard for atomic mass is carbon 12. It is carbon 12. And we need a unit also to get the atomic mass. The unit for atomic mass is known as atomic mass unit, AMU. And the unit, AMU, atomic mass unit, that is 1/12 of the mass of a carbon 12 isotope. First of all, we are taking carbon 12 as the standard for the atomic mass. The modern standard for atomic mass is a carbon 12. Then 1/12, 1/12, 1/12 of the mass of a carbon 12 isotope is taken as the standard. That is the unit, it is taken as the unit, and it is known as atomic mass unit AMU. So 1 AMU, that's equal to 1/12 of the mass of a carbon 12 isotope. And what will be this mass in gram? This mass in gram is equal to 1.66 into 10 raised to minus 24 gram, same as 1.66 into 10 raised to minus 27 kilogram. 1.66 into 10 raised to minus 27 kilogram, that is the mass of a 1 AMU, 1 atomic mass unit. In kilogram, the mass is 1.66 into 10 raised to minus 27 kilogram. See here, 1.66, that is the digit form. That is the digit form. Say last day, we had seen the scientific way of expressing a number, scientific or exponential form. The exponential for a scientific representation. Two parts are there. Capital N into 10 raised to small n. And that the capital N, that is the digit. And the small n is the exponent. Here in 1.66 into 10 raised to minus 27. Here 1.66 is the digit part, the digit form. And minus 27, that is the exponent. And that is the importance of the exponential notation or scientific notation of a number. You got it? So there is an example here. So coming back to atomic mass, as I told you, it is only a relative mass. And to get the relative mass, we need a standard. The standard, modern standard for atomic mass is carbon-12 isotope. I repeated again. The modern standard for atomic mass is carbon-12 isotope. And the unit for atomic mass, is 1/12 of the mass of the carbon-12 isotope. And that is called the 1 AMU, atomic mass unit. So 1 AMU, 1 atomic mass unit, is equal to 1/12 of the mass of the carbon-12 isotope, and that's equal to 1.66 into 10 raised to minus 27 kilogram. All right. Here we can give the definition for atomic mass. Atomic mass is the ratio between the mass of an atom and 1/12 of the mass of a carbon-12 isotope. The ratio between the mass of an atom or the element and the 1/12 of the mass of a carbon-12 isotope. So you can write atomic mass in the form of an equation like this. That is what is given to you. Atomic mass is equal to mass of an atom by 1/12 of the mass of a carbon-12 isotope. That is the definition given to you. Now you come to some examples. Say atomic mass of hydrogen is equal to 1.008 AMU. And it can be approximated as 1 AMU. When somebody speaks about the atomic mass of hydrogen, immediately you will say, atomic mass hydrogen is equal to 1. Not simply 1, you say 1 AMU, 1 atomic mass unit. To be more exact, it is 1.008 AMU. The same, similar you take carbon. Atomic mass carbon is equal to 12 AMU. 12 AMU. You come to oxygen. Atomic mass of oxygen is equal to 16, you say. Actually, it is 16 AMU, atomic mass unit. And what is the meaning of this? Atomic mass hydrogen is equal to 1.008 AMU. That means one atom of hydrogen is 1.008 times heavier than 1/12 of a carbon-12 isotope. Similarly, when you say atomic mass of oxygen is equal to 16 AMU, the meaning is this: one atom of oxygen is 16 times heavier than 1/12 of an atom of a carbon-12 isotope. That's the meaning. But majority of the atomic masses of elements are found to the fractional values. As it is seen in the case of hydrogen, it is 1.008 AMU. Or for oxygen, to be more exact, it is 15.99 AMU fractional values. You come to chlorine, the atomic mass of chlorine, as you know, it is equal to 35.5 AMU fractional values. And what's the reason for these fractional values? You can say Hari, what is the reason for the fractional values of atomic masses? Only after that we can proceed. Say, do you get me, Hari? Say, Hari.
Yes, sir.
If you get me, you give the answer.
I don't know, sir.
You know, it's all right. I shall help you. Say, there are isotopes. For elements, there will be isotopes. And you know what are isotopes? We'll take the topic again. There is another chapter. In that chapter, we'll be taking the isotopes again. Say, okay. So, isotopes are the different atoms of the same element. So, what is the difference? The difference is in mass. So, the various atoms of the same element with the different masses, you have studied that Isotopes are the atoms with the same atomic number, but different mass numbers. You have studied that atoms with the same atomic number, but different mass numbers. The meaning is this: these are the atoms of the same element. These are the atoms of the same element, but they have different masses. The mass numbers will be different. And such atoms are called isotopes. Now, do you get me, Hari? Atoms of the same element, but the atoms are having different masses. So, atoms with the different masses of the same element. That is why we say they have same atomic number. If atomic number is the same, these are the atoms of the same element. Because an element is determined by its atomic number. All right? An element is defined by its atomic number. So atomic number same means same element. Mass number is different means the atoms are having different masses. All right? Okay. So due to the presence of isotopes, elements have the fractional atomic masses. The isotopes will be having different proportions. So after giving the due weightage to the various proportions of the different isotopes, you have to take the average mass of the masses of the isotopes, so that the average mass becomes a fractional value. All right, Hari? Aditya? All right? So the fractional values are due to the presence of the isotopes. After giving due weightage to the various isotopes, we are taking the average value, so that the atomic masses will be fractional values. All right. Let me proceed to the next point. That's about molecular mass. Come to the molecular mass. Like atomic mass, you come to molecular mass. Just like our atomic mass, molecular mass is also not the exact mass of a molecule. That is not the exact mass of a molecule, of an element or a compound. No. These are also relative masses. Here also we have to make use of a standard. Here also the standard taken is carbon-12 itself. So carbon-12 itself. And the unit is 1/12 of carbon-12 isotope. And if you call this value as atomic mass unit, it may have some, say, negative interpretation when you deal with the molecular mass. So the term atomic mass unit AMU was substituted by another term, unified mass, that is U, unified mass U. In unified mass also, the standard is carbon-12 itself, and the unit is 1/12 of the mass of a carbon-12 isotope. There is no doubt. But we are changing the term from AMU, atomic mass unit. We are using a more general term, unified mass U. So unified mass can be applied in the case of both atomic masses as well as the molecular masses. Now let us come to the definition. Let us come to the definition of molecular mass. Molecular mass is the ratio. That is the ratio between the mass of a molecule, a substance, to 1/12 of a carbon-12 isotope. Okay, that definition you need not study for the time being, you just leave it. But we can study the definition like this. Molecular mass is, see, molecular mass is the total sum of the masses of various atoms. The various masses of various atoms, masses of atomic masses of various atoms present in a molecule, present in a molecule. It is the sum of the other definition you just forget. You remember this definition. Molecular mass is the sum, the total, the sum of the masses of various atoms present in a molecule. So to get the molecular mass of a substance, maybe an element or maybe a compound, you just add all the atomic masses so that you will get the molecular mass. Say, for example, you calculate the molecular mass of methane. Say, example, methane, molecular mass of methane, that is our methane. You have studied methane. The molecular formula is CH4. CH4. That's the molecular formula of methane. And what is the molecular mass of methane? Say, just above, there is the definition. You just add the atomic masses. So, one molecule of methane, that is a CH4, there is one atom of carbon and 4 atoms of hydrogen. So, atomic mass of carbon, that is equal to 12 AMU. There is only one atom, so 12 into 1 plus then hydrogen. Atomic mass of hydrogen is equal to 1 AMU, 1.008. You just approximate it as 1 for simplicity. So 1 into, there are 4 hydrogen atoms, so into 4. And this is equal to 1 into 12 into 1, 12 plus, then 1 into 4 is equal to 4, and that is equal to 16. Now you write the unit U. You write the unit U, not AMU. That is why we replace the AMU to U. AMU is better applicable only in the case of the atomic masses. But U, unified mass, can be used in both the cases. There is no problem. We can use in the case of atomic mass as well as molecular mass. So molecular mass of methane CH4 is equal to 16U. Similarly, you calculate the molecular mass of water. Say molecular mass of water, you know the method now. Water, molecular formula is equal to H2O. You add all the atomic masses. Hydrogen, atomic mass is equal to 1. And here there are, Krishna, do you get me? Eh? Say Hari, Punya, all of you get me?
Yes, sir.
Let me proceed. Say, atomic mass of hydrogen is equal to 1. There are 2 hydrogen atoms. So, for 2 hydrogen atoms, 1 into 2 plus atomic mass of oxygen. As you know, it is 16. There is only 1 oxygen atom. So, 16 into 1. And that's equal to 1 into 2 is equal to 2 plus 16 into 1 is equal to 16. That is equal to 18U. 18U. That is the molecular mass of water. So we can calculate the molecular mass by simply adding the atomic masses of the various atoms, various types of atoms present in the molecule. That is equal to the molecular mass. All right? Okay. Now, let us think of another term that's called formula mass. That is called a formula mass, a term called a formula mass. And what is formula mass? Formula mass. See, where we can see the significance of a formula mass. In some cases, there are ionic compounds. Ionic compounds. In ionic compounds, we cannot write actually the molecular formula. We can write only the average formula. And there we make use of the formula of the ionic compounds. And the formula mass finds significance in the case of ionic compounds. So there is a significance, more significance is seen in the case of ionic compounds. This is more for ionic compounds. This is similar to the molecular mass, but this is more applicable in the case of ionic compounds. And how will you get the formula mass? To get the formula mass, what you have to do? You simply add the atomic masses in the formula. The formula will be given to you. Formula of the compound will be given to you. And as before, as in the case of a molecular mass, you simply add up. The atomic masses. So formula mass is the sum. It is the sum of the atomic masses. Atomic masses of various elements. Atomic masses of the various elements. So that is same as in the case of molecular mass. But molecular mass is mainly for the covalent molecules, and this is mainly for the ionic compounds. There is no difference at all. Say, for example, you take the molecular formula of sodium chloride. As you know, sodium chloride is composed of sodium Na plus ions and Cl minus ions. Sodium chloride. The formula of sodium chloride is NaCl. Actually, it is not the NaCl. If you are writing the formula like this, you may feel that sodium chloride is composed of sodium atoms and chlorine atoms. No. There are no sodium atoms or chlorine atoms, but there will be sodium ion and chloride ion. But for simplicity, we just ignore the charges, that's all. You just ignore the charges because the charges will be nullified, will be neutralized. And so we are not writing the formula. The actual formula of sodium chloride is Na plus Cl minus, and for practice, we write it as NaCl. So what will be the formula mass of sodium chloride? What you have to do? Here it is, the sum of the atomic masses of the various elements. Here we have sodium and chlorine, and so atomic mass of sodium. All these atomic masses you will study in the coming periods. You will study atomic mass of sodium, that is equal to 23. There is only one sodium ion, so into 1. 23 into 1 plus atomic mass of chloride, that is coming from chlorine. Atomic mass of chlorine, that is equal to 35.5. There are only one chloride ion, so 35.5 into 1. You add this, you will get 23 into 1 is equal to 23 plus 35.5 into 1, 35.5. And this value is equal to, you add this, you will get 58.5 U. 58.5 U. That is the formula mass of sodium chloride. It may be read as molecular mass also. There is nothing wrong in that. Even if you are calling it as the molecular mass, there is nothing wrong. But to be more specific, it is called the formula mass. So formula mass comes into play when we deal with the ionic compounds. Okay. All right. You follow this? May I proceed? You say yes or no?
Yes.
Okay. Now, let us think of another term that is called mole. You have studied about mole. mole. The symbol, as you know, it is mole. M-O-L, mole. You know what is mole? Mole is a unit used to express the amount of a substance. Remember the SI units, The amount of a substance can be expressed in terms of moles. The symbol is a MOL, mole. And what is a mole? How can we define mole? The one mole is the amount of particles. The amount of particles may be atoms, may be molecules, may be ions, whatever it is. The amount of particles equal to the number of atoms in 12 grams of carbon-12. It is the amount of a substance. Amount of a substance, which is equal to, in number, it is equal to the number of atoms present in 12 grams of carbon-12 isotope. 12 grams of carbon-12 isotope. So the amount of particles, atoms, molecules, or atoms, molecules, or ions, whatever it is. So the amount of particles, we simply say particles, number of particles. The particles may be atoms or may be molecules or ions. So the amount of particles equal to, the number of particles equal to the number of atoms present in 12 gram, present in 12 gram, present in 12 gram of present in 12 gram of present in 12 gram of carbon-12 isotope. Carbon-12 isotope. Say you take 12 gram of carbon-12 isotope. 12 gram of carbon-12 isotope. 12 gram of carbon-12 isotope. You take 12 gram of carbon-12 isotope. Okay. So amount of particles equal to the number of atoms, equal to the number of atoms present in 12 gram of carbon-12 isotope. 12 gram of carbon-12 isotope. So here also the standard is carbon-12 isotope, remember. Atomic mass, molecular mass, mole concept, everywhere we can see carbon-12 isotope is the standard. Okay. So you take a 12 gram of carbon-12 isotope. And how many particles will be there? What will be the particles in carbon-12 isotope? The particles will be atoms. That is why we have written the amount of particles, number of particles equal to the number of atoms present in 12 gram of carbon-12 isotope. In 12 gram of carbon-12 isotope, there will be, say, a definite number, a fixed number of atoms. And that number will be 6.022 into 10 raised to 23. So much atoms will be there. If you take 12 gram of carbon, there will be 12 gram of carbon-12, not simply say carbon. 12 gram of carbon-12, there will be 6.022 into 10 raised to 23. So much atoms will be there. So what will be 1 mole? So 1 mole is equal to the amount of particles, equal to 6.022 into 10 raised to 23 atoms. This number. And this number has a special name. And that number is called, Avogadro number. Do you remember? Avogadro number. It is also known as Avogadro constant. Avogadro constant. And it is represented by Na. N for number, and A for Avogadro. N for number and A for Avogadro. So 1 Avogadro number, that means 6.022 into 10 raised to 23. That number. So much number of particles are taken. And what will be the amount of this much a number of particles? And that is called 1 mole. So 1 mole of a substance is the amount of particles equal to the number of atoms present in 12 gram of carbon 12 isotope. But in 12 gram of carbon 12 isotope, there are 6.022 into 10 raised to 23. 10 raised to 23. So much atoms are there. And this number, that's a constant value, and it is known as Avogadro number, known after the scientist Avogadro. Avogadro number or Avogadro constant, and it is denoted by Na. N for number and A for Avogadro. So we can say 1 mole is equal to the mass of 1 Avogadro number of particles. The mass of 1 Avogadro number of particles. That is the amount of 1 Avogadro number. 1 Avogadro number of particles. That is equal to the amount of, what is a Avogadro number? 6.022 into 10 raised to 23. So much particles. The particles may be atoms, the particles may be molecules. If you are taking 6.022 into 10 raised to 23 atoms, that is equal to 1 mole of atoms. If you are taking 6.022 into 10 raised to 23 molecules, that is a mole of molecules. Same, 1 mole of atoms, a small heap. 1 mole of molecules, a larger heap. The meaning of mole is heap. That's the meaning. And what will be the amount? The amount will be the same as 1 atomic mass of the element expressed in gram, or it is the same as molecular mass expressed in gram. So this is equal to 1 what is it? The atomic mass. 1 atomic mass expressed in gram, or it is 1 molecular mass expressed in gram. That is the same as 1 mole. I repeat the whole thing. What is a mole? 1 mole is the amount of particles, atoms, molecules, ions, etc. The amount of particles equal to the number of atoms present in 12 gram of carbon 12 isotope. But in 12 gram of carbon 12 isotope, there are 6.022 into 10 raised to 23 atoms. And that number is called Avogadro number or Avogadro constant Na. So we can say 1 mole is equal to the amount of one Avogadro number of chemical units. Or it is the amount of 6.022 into 10 raised to 23 chemical units. The chemical units may be atoms, molecules, or ion C1, or electrons, protons, whatever it is. This is just like one dozen. We give importance to the number only. 1 dozen is equal to 12 numbers. 12 numbers. Similarly, here also 1 mole, that is related to the number of atoms, number of molecules, number of ions, number of electrons, number of protons. How much? 6.022 into 10 raised to 23 atoms. That is equal to 1 mole of atoms. 6.022 into 10 raised to 23 molecules. That is a mole of molecules. 6.022 into 10 raised to 23 electrons. That is a mole of electrons. 6.022 into 10 raised to 23 protons. That is a mole of protons. So the importance is for this number, Avogadro number 6.022 into 10 raised to 23. And that number is the number of atoms present in 12 gram, exactly in 12 gram of a carbon-12 isotope. That's all about today's class. Do you follow all this? Okay. Any problem? No response. What happened? You are not there. Yeah,
Yes.
you already quit. You say the reply.
Yes.
Okay, you follow?
Yes.
So 1 mole means the amount of particles equal to the number of atoms in 12 gram of carbon-12. But in 12 gram carbon-12, there's a fixed number of atoms, 6.022 into 23 atoms. That is called Avogadro number. So the mass of the amount of 6.022 into 10 raised to 23 particles, atoms, molecules, or electrons or protons, whatever it is, that is called 1 mole. And in terms of the masses, 1 mole is equal to 1 atomic mass in gram. It is the same as the mole of atoms. Okay, 6.022 into 10 raised to 23 atoms. That is equal to 1 mole of atoms. And it will be having 1 atomic mass expressed in gram. And 1 mole of molecules. That is equal to 6.022 into 10 raised to 23 molecules. And the mass will be equal to 1 molecular mass expressed in gram. That's all for today. Let me stop now. Thank you. Meet again.
Excuse me, sir.